recorder, and we are ready to go. Okay. All right, so first thing first, we do have a homework assignment because I know some of you know that we need to have more homework assignments. So here's a new one. Array 1 is a new homework assignment. So we'll go over this one first because it is kind of important to go over this one. The instruction has changed. I'm still trying to collect all the bits and pieces for the previous two homework assignments because Canvas just could not work with the links that are not working 100%. So I still have to work that part out. So that's why I'm changing the way we turn in homework assignments. Not really a whole lot. The way we do it is we still use a spreadsheet and we use a table to do everything, except we are not going to use Google Spreadsheet anymore. Instead, we'll use LibreOffice. Okay, so that's why you have to follow these instructions kind of carefully in the homework description. For the most part, the chore is just to set it up the first time. After you set it up the first time, all the other homework assignments will be much easier. So I'll go over this step by step just so that we know how to get it set up. The first thing you need to do is to go get LibreOffice. Okay. So this is the name of the Office suite that I want you guys to use. It is open source, which means if you do not have it installed on your computer, you can get it for free and it will install in Windows, Mac OS X, as well as Linux. So unless you have some really oddball operating system that I do not know of, in which case you probably don't need this class, I think you'll find one of these versions will install. So there are two subcases too. If you are on campus, let's say in the library, or you're working on a computer where you do not have administrative right to install any software, you will need to use LibreOffice Portable. So I'll go ahead and go to the portable. Let me see. I'll just click on this link here. Right click, new tab, and it opens it up over here. There we go. So this is what we call a portable version of LibreOffice in this case, but you can find portable versions of just about anything. Just about anything that is open sourced has a portable version. So the portable version is nice because you can quote unquote install it on a thumb drive. So you can get a really small thumb drive, 4, 8 gigs should be fine, and you can quote unquote install LibreOffice Portable on that thumb drive. So now you can take that thumb drive and plug it into any Windows machine, including the ones in the library or the ones over at the STEM Center or the ones in our lab here, and you can run the program from the thumb drive. You don't need to install anything on the computer itself. Is that okay? So this is great if you need the portability. So even if you have a computer at home where you can install the regular version of LibreOffice, but if you think that you might want to work on your homework assignment, a few days in a day, a few days in a week, where you'll be working with a computer that may not have LibreOffice installed, you still want to kind of look into the portable version of LibreOffice. Is it okay? All right. So the instruction to install this is actually included here. If you just kind of follow, let's see here. Yeah, it's really just running the program and directly to unpack all the files onto a portable drive, and that's it. Okay, so from that point on, you go to the folder on your thumb drive, double click on the application, and it will start from there. On the other hand, if you say, I have my own laptop computer that I carry with me all the time, then you can just go ahead and use the usual version of LibreOffice. So to go there, you follow this link, and it will give you this page. So the browser automatically detects what operating system I'm using. So it's picking the 64-bit of Linux that's actually suitable for this computer. But when you click the drop down, you can see the other versions. So if you're using Windows, you probably want to use the 64-bit of Windows because most people use 64-bit Windows these days. There are only very few people using the 32-bit version, which is the one before. If you're using Mac OS X, obviously use the Mac OS X version of LibreOffice. So do we have any questions about where to get LibreOffice or how to install it? Okay, no questions? Good. So once we have LibreOffice installed, the next step, now obviously this step only needs to be done once, right? Because once you have installed it, you're all set up. The second step is here, open up LibreOffice and then go to the Tools menu and then select Options and then enter your own information into the user data. So I'll show you what I mean by that. Mine is not going to look exactly the same as yours, but it will be close enough for all practical considerations. So I go to my office, I open my LibreOffice. It doesn't even have to be a particular application. It's asking me how to save the old documents. So you can basically, you will see something like this if you're not specifying a particular application. Go to the Tools menu and then go down to Options, which is here. Click on that one. And then the first thing you want to enter is just user data. I don't need to know your address. I don't need to know your phone number. All you really need to enter would be your first name and last name. So just enter your first name and last name, kind of like that. Make sure you click OK, and then you can close it. So from now on, all the documents that you create, all the documents that you edit will leave behind a quote-unquote fingerprint that has your first name and last name on it. Okay, so that's what I want, okay? Do we have any questions about this particular step? The instructions is also described here, okay? So what I just did is also described here. So now the third step is to download the quote-unquote source document or the document that you start with. So you just right-click on this, okay? I would not just click on it because if you click on it, the browser will try to open the document automatically for you, which is not what you want, okay? So what you want is to save the document first. So you click on Save Link As or Save Target As, depending on the browser, and specify a position or location that you know where you're going to put it. So I'm going to just put it into my Downloads folder. And now the document is saved locally. And then what I need to do is to open LibreOffice using Calc, or just LibreOffice is fine. So from here, I go to File, I go to Open, and then I go to LibreOffice again. Okay, where is it in here? Array 1, there we go. So double click on it, and it opens up the document. So do we have any questions about the procedure to open the document? It's really just like using Microsoft Office, except I don't want you to use Microsoft Office. Okay? All right. So once you are here, this tab, which is Code, is basically giving you the algorithm that you have to follow. And then the other one is Trace. And I have the columns already pre-formatted because you will need to know the size of the array. So this tells you how many elements are in that particular array? 4. Oh, 5 elements. You're correct. There are 5 elements. There are 5 elements because the index of the last element is the number of elements minus 1. So that means, if the index of the last element is 4, there are actually 5 elements in the array. And you can also see that A occupies D, E, F, G, H. It occupies 5 different columns. So that's another clue that we have an array of 5 items. So are we good so far with how to get started with this homework assignment? Yes? Okay. So when you trace this particular algorithm, you have to follow all the usual rules that we have to use. The other thing that you also want to know is how do I display the algorithm and also the trace at the same time. This time it is a whole lot easier than last time, okay? Because what you do is you go to Window, you just click New Window, that's all. So when you click New Window, it will open up another window of the same document. So now one can be on Code, the other one on Trace. Now you have 2 views of the same document. So it's much easier to track what code you're executing when you use LibreOffice. So do we have any other questions about this part? Nope. Okay. So I think once I save the document, save the video, and you guys have a chance to review it, the step-by-step instructions should be fairly clear. If not, you can let me know and I can help answer questions of how to set up LibreOffice. So back to the instructions a little bit more. Any submission using any other means to work on the document will not be graded. So I don't want to take anything that is edited in Excel. Okay, so don't use Excel to work on this document. That's the bottom line. Don't even let it touch it. Okay, and that's why, right click on the document, save it first. Don't use the browser to open the document. If you did, then more likely than not, Microsoft Office is going to open it, because many of you already have Microsoft Office installed, and Microsoft Office does recognize ODS as an extension. So it's going to hijack and say, oh, I know how to open this document, and then that's going to ruin it. Okay? So don't do that. Save the file first and then open LibreOffice, and from LibreOffice open the document. Okay? There's a lot of don't. Okay? So do not work on this document using Excel and then copy and paste it into the LibreOffice document. Work on the document using LibreOffice. Is that okay? So right here, I said do not use Excel at all. Just don't let Excel touch it. Also, do not use Google Sheet. The bottom line is the only software you should use is LibreOffice to work on this document. Are we clear? Does everybody know the difference between Excel and LibreOffice? So you can tell which one you're in. Okay, all right, very good. When you're all done, in this case, you're not sharing a URL with me, which caused a lot of problems with homework assignment 1 and 2. For this one, you just upload your ODS document back onto Canvas, and that's it. Okay, so I think this time it will save us a lot of trouble, even though setting up may take a little bit longer. But I think in the long run, this is a better way for me to kind of grade your homework assignment. Any questions at all with regard to how to install LibreOffice, how to use it, and how to turn in your homework? Okay, no questions? All right. So in this class, I will also use LibreOffice. So this way, you can ask questions, okay? As I use LibreOffice, you can ask questions of, okay, how did you just do that, okay? So I can show you, how to set up LibreOffice correctly to do your homework. I don't think there's any real trick to it, but if you do have any questions, we can, I can address those questions. Are we good so far? Okay, all right. So if we are okay with the assignment, we'll go back to Introduction to Arrays, which is where we left off last time. And I think last time, did we finish the entire algorithm of finding an element? We did not finish the whole thing. Okay, I remember now. We did not finish the whole thing. So what we'll do is we're going to go back to the video first and watch the very, very last part of it, so that we can kind of know, which part of the program or where we left off last time on Tuesday. So this is the very last part of the discussion on Tuesday. And there we go. Okay, so let me pause over here. Can everybody read from the video itself? People from the back especially, can you read it? Okay. So what we have done is we have worked it up to this point. So I'm going to copy that into today's notepad. Okay, so you don't have to read a smaller font like this for the rest of the class. But this is where we left off. So let me just kind of copy it by hand first, and then we'll start with this one and try to find out what is the problem of that code, because that code has a little bit of a problem, but it's a very obscure problem where if I don't say it, or if I don't let you know, most people would not be able to spot that problem. So the first thing I'm doing here is really just to copy the code as it was on Tuesday. Okay, so here's the code that we worked on Tuesday. I can now close my YouTube tab. And I apologize for not releasing the video because I forgot to make it public. But what we want to do is to say, well, this looks okay to me. I don't really know why this code is not correct. Okay, that's probably not an uncommon question because it does look right. Okay, because we derived this algorithm on Tuesday step by step. So one way to find out what may be wrong with this code is to test it. Okay, so we're going to test this code, which also gives us a very good opportunity of looking at LibreOffice and see how we can use LibreOffice to trace the execution of a program. Okay, is that okay? All right, so we're going to have to set up a spreadsheet. Okay, so I cannot use the same as the homework assignment because I want to leave that one as it is. So I'm going to open a new document to work on this one. So let me close the other two. Okay, so I'm closing the other two spreadsheets. And in this case, because we do have the algorithm on one side already, I'm not going to copy the algorithm into the spreadsheet. So I will start with the trace here. So we have comments, we have line number, we have three, we got 1, 2, and we got 2 normal variable and the array. So one normal variable is I. Okay, so we have the first problem now. Did you see how I type lowercase I and then LibreOffice turns it into uppercase I? Because it thought I had a typo. Because it thought that I means me, self, and it should be capitalized. So what we can do is to turn that off. Okay, if you want to turn off or customize all the autocorrect options, you go to Tools and then you go to autocorrect options. And it has a whole lot of options here. Replacement table would still be good to use. You can turn off replace dashes and the other ones. The replacement table looks like this. And you can look under I, which is the lowercase I, and this is replaced with the uppercase I. You can delete an entry if you want to. Okay, and this is the one that I would do because I use the variable name I a lot in programs, so I would just kind of delete it. And then you click OK. You only have to do it once because once you have done it, it will remember it. Okay. So we have local variable I, not local, but variable I, variable K, and then we have an array. We don't need a really big array to illustrate the point that I want to make. So I'll just make this array size of 2. Okay. And this is array bracket 0, and this is bracket 1, which means this is the first element or element 0. This is the second element, which is element 1. Are we okay so far? You can see this is kind of resembling your homework a little bit, right? Yes, go ahead.
What's the shortcut for merging cells?
The shortcut keys that I used was, so when I had both cells selected, it's Alt-O to go to the format menu, E to get to merge cells, and then M to get to merge cells. It is now grayed out because it's already merged. So that's why you saw OEM, because I did not click the Alt key correctly, so it just typed OEM into the cell. Okay. All right. So on the pre-line, we have certain assumptions that we have to make in this case. The I is question mark because the first thing we do on line 1 is to overwrite it, so it doesn't make any sense to make any assumption. But K and all the content of array A, we kind of need to make some assumptions here because we are supposed to be finding a particular value in the array A. So we will start with a case where we can find it and see what happens. Yes?
How do you know that there are 2 elements in the array A?
I just make the assumption. That's something I have to make up. So in order to make this demonstration not too long, 2 elements would be sufficient. That's a good question. All right, so let's just say that we're looking for a value of 3 in the array, and in the array, the second element has a value of 3. Okay, so these are assumptions, and that's why they all belong to the pre-line, because I have to make the assumptions, otherwise the algorithm, I cannot execute the algorithm. Yep. I just made it up. It's part of the assumptions.
Would we do that on our homework as well?
When you do your homework, you would not have that issue because the algorithm that you have to track is not this one. So the algorithm that you need to track does not need any assumptions. So in your case, every single column should be unassumed, which means they should all be unknown to begin with. Okay, that's a good question. Okay, very good question. So line 1 is just initializing I to 0. On line 2, we evaluate the condition, which is kind of long. So we have to say, does k equal to a bracket I? Or are they different, I should say? Is k different from a bracket I, true or false? That's the question. K is 3. Okay, we got that. What is I? I is 0 at this point. So a bracket 0 would be referring to which column? It will be referring to column E, which has a value of 1. 3 is not the same as 1 is true. Okay, very good. But we are not done yet because this is a conjunction. If the first part or the left-hand side of a conjunction is true, can we conclude the entire conjunction is true? Not yet, right? So we have to look at the right-hand side as well. The right-hand side says, is I less than bar A bar? I is 0. What is bar A bar in this case? It should be 2 because there are 2 elements in array A, so bar A bar should be 2. Is 0 less than 2? True. Okay, so we have true and true, which means the conjunction is true. Okay, so now I can just write the whole thing, and I is less than bar A bar is true. So you may not run into this problem of needing more space for comments because the code that you need to track does not have a complex condition like this. Where do we go? The while condition is true, so where do we go? We go into the body of the loop, right? So we go to line 3. And what does line 3 do? Just add 1 to I, right? I goes from 0 to 1. Then where do we go? Go back to line 2 and reevaluate the condition. So when you reevaluate the condition, k has not changed. There's a question? Oh, okay. So k has not changed, which is still 3. What about I? What is I now?
1.
I is 1, so a bracket I refers to a bracket 1, which is which column?
F.
Column F, which has a value of?
0.
No.
1.
1, no.
No, you said A bracket F. That has
A bracket I
Oh.
is a bracket 1, right? Because I has a value of 1.
That's 3.
It has a value of 3.
The problem you're having is the column's not.
Yeah.
Oh, darn it. Sorry about that. There you go. Oops. Better? Okay, there we go. I apologize. Okay, so now that we know that a bracket 1 is also 3, k is 3, 3 is different from 3 is false. Okay. Now, this is the part where it looks a little bit odd because I can now just say this is false. Then you go like, what? Tack, aren't you a little bit lazy? And my answer is absolutely. Okay, the answer is absolutely. I am lazy as it can get in this case. Because this is a conjunction, right? In a conjunction, if I know the left-hand side is false already, can the conjunction itself be true? No. So that means it is conclusive. Knowing that k does not equal to a bracket I is already conclusive that the entire conjunction is false. And I stop here. I do not even bother to check whether I is less than bar A bar because that is not necessary. So I will talk about this technique in details a little bit later. So right now we just say that this is called the lazy evaluation method. But it has a longer, more technical term later on. The longer technical term, by the way, is called short-circuited evaluation. So when you encounter those terms referring to the evaluation of either or and, it is called short-circuit evaluation, which means, well, if we find a shortcut, we take the shortcut and we say, okay, we're done. It is also called, casually call it lazy evaluation because we are just saying, oh, since we know the answer already, I'm not going to bother with the other side. Okay, so we'll talk about this in detail a little bit later. But the conclusion is the condition is false on line 2. So where do we go when the condition is false on line 2, which is like a while condition? Yep, we're done. Post. We're done. Okay. So do we have any questions about this trace? I hope not, because there are no new concepts. Yep, go ahead.
I know you already said why you chose 3, but like, why 3 out of all numbers?
Why?
Why did you choose 3?
For k? Just so that I can illustrate what happens when you do find something that you want to find in the array. Yep. So the next one, that's a good question, because the next one is going to be, what if the element we want to find is not in the array? Okay. So let's work on the next test case. Okay. So I'm also being very lazy here because I'm just copying and pasting the entire trace. But this time I intentionally want to find something that is not in the array. Okay. So I'm going to make k 4 this time. So we'll follow the same algorithm. Line 1, I gets initialized to 0. Line 2, we ask the question of k does not equal to a bracket I. Is that true or false?
True.
K is 4, right? I is 0. So a bracket I is a bracket 0, which has a value of 1. 4 is different from 1 is true. Okay, so that's the long way of spelling it out. Is I less than bar a bar? I is 0, bar a bar is 2, 0 is less than 2 is true. So we got true and true, so this whole thing is true. No problem. We get to line 3, we add 1 to I. I goes from 0 to 1. We go back to line 2. K is 4. 4 is different from a bracket I, which is 3, is true. Okay. Now I look at the other one, which is, is I, which is now 1, less than a bar, which is 2. What do you think? True. Okay, so both are true, so the conjunction is true. Then we go to line 3, we add 1 to I. Now we get back to line 2, and now we have a problem. Because the first question we ask is whether k is different from a bracket I. What is I again at this point? A is 2. Where is a bracket 2? There is no such thing. Very good. Okay, there's no such thing as a bracket 2 because A is an array of 2 elements. There's no third element. So when I need to ask for that element to do the comparison, I have a problem. Okay? Now the problem can manifest in one of 3 ways depending on your programming language. First, if you're doing this in Visual Basic or C#, it will give you a runtime error. The program would actually stop execution, pop up a dialog box, and says array access out of bound or something along that line, and it might even give you a line number, and the program would just stop, which is the best response from a program. The second way, for most scripting languages, is if you try to refer to an array element that does not exist, it will create it on the fly. In other words, a bracket 2 will come into existence right now. Okay? But you will say, but we did not initialize the value of a bracket 2. What is it going to be? In some scripting languages, they have a specific value, which is called nil, that refers to a variable that is not initialized. Okay? But that is not what we want either. Okay? The third case is what you will encounter in C and C++, which is basically the reason why you are here at this point. Okay? In C and C++, it will just take the next column, which is column G, and treat it as if it is a bracket 2, even though it is not. Okay? Which is the worst possible way of handling this situation. But that's what C++ is going to do. Okay? But since we are tracing it by hand, we will now say that cannot be done. Okay? So we'll just say in here and say cannot be evaluated. And then we'll just stop here because the program cannot proceed past this point. In fact, okay, let me go here, and I'll even just change the font color to red, to indicate that we have a problem. Is that okay? I mean, is it okay from the perspective, do you understand that we have an issue? Because we are trying to access an element that does not exist. Okay? So, but it is not okay from the perspective of the algorithm because, hey, if I write an algorithm like this and run it in C and C++, it will accidentally, it will try to evaluate, it will try to use whatever is in column G and pretend it is A bracket 2 and actually do the comparison, which is not the right thing to do. So now the question is, how do I fix this program? Yep.
If you added a conditional statement, would that fix it? As in, I would be less than a bar.
You will have to separate those two, right? I mean, so the idea is we cannot, if we cannot be sure that I is within the correct bound, which is less than bar a bar, we really should not use it as an index, right? Remember what we talked about just before running this particular program? We were talking about short-circuited evaluation, right? So do you think short-circuited evaluation can help us in this case, given that we changed the program just a little bit? Okay, probably. So now we look into, okay, so if that's going to help us, how are we going to do it? Okay, so let me give you the second version of this code where the change is very minor, but it will fix the problem. The change I'm going to do is simply to reverse the two sides of the conjunction. Okay, so when you look at the new line 2 versus the old line 2, the only change is what was on the left-hand side is now on the right-hand side. What was on the right-hand side is now on the left-hand side. But I claim that this is going to fix the problem, even when you're looking for a value that is not in the array. Okay? So let's find out how this is going to help us. So we'll make a copy of this stuff here. I'm not going to overwrite this trace here. So I'm going to make a copy of all of this, make a new sheet, and then start the trace from the beginning again. Okay, get rid of all this stuff, starting on line 1. So remember, we are now looking at the second algorithm, not the first one. Okay, so line 1, okay, no change over there. Line 2 doesn't seem to make that much of a difference because at this point I is 0, bar a bar is 2, 0 is less than 2 is true. Okay, but since it's in a conjunction, we have to look at the right-hand side. The right-hand side will give us, k does not equal to a bracket I. K is 4. A bracket I refers to a bracket 0, which has a value of 1. 4 is different from 1 is true, right? So now we have true and true again, and the answer is just true. Are we good so far? So we haven't really seen any major differences of this trace compared to the previous one yet. Okay? We go into the loop body, we increment I, so it goes from 0 to 1. We go back to line 2. I is now 1. 1 is less than 2 is still true. Okay, and we look at k, which is 4. Is it different from a bracket 1? A bracket 1 still has a value of 3. 4 is different from 3 is true. So now we have true and true again. So this entire thing is true. Okay? So far we haven't seen any differences in terms of the behavior of the program compared to before. So we go to line 3 again. We add 1 to I. You might say, uh-oh, here we come. We are going to do something bad again. Not really, because the first comparison is between I and bar a bar. Is I less than bar a bar at this point? No. It is not. It is false, right? So if it is false and you combine this with the short-circuited evaluation method, what are we going to do to the right-hand side of the conjunction? Absolutely nothing, right? Because we are trying to be as lazy as possible. If one side of conjunction is known to be false, the whole conjunction is going to be false anyway. Why would I want to waste my time to evaluate the right-hand side? So I have now conclusively determined that the conjunction itself is going to be false. I don't have a problem anymore. Do you see how reversing the order of the the two sides of the conjunction, and using short-circuited evaluation is helping us to solve this problem. Okay? Now, it looks really kind of magical, right? Because it's like, wow, we just flip the order of something and we don't have a problem anymore. We get to post and we're all done. Is that okay? Does everybody understand what just happened? The two things that fix this particular problem. The first thing is we introduced the concept of lazy evaluation, otherwise known as short-circuited evaluation, which basically says if you have a conjunction, if the left-hand side is false, then you don't even bother to evaluate the right-hand side. You just say the whole thing is false. That's the first thing. The second thing has to do with what do we use as the left-hand side and what do we use as the right-hand side of this particular conjunction. Now that one you have to be careful, because what we are doing here is we are using the left-hand side, basically limiting the value of I to as a quote-unquote guard condition for the right-hand side. Let me say that one more time. We're using the left-hand side of the conjunction as a guard condition for the right-hand side. What that means is we don't bother with the right-hand side unless the left-hand side is true. But what does it mean when the left-hand side is true? I is still a valid index. Is that okay? So I don't bother to look at the element at index I unless I is guaranteed a valid index. That is the magic of this particular statement, or the way we arrange the conjunction. Do we have any questions about this part? No? Okay. This is one, yeah, go ahead.
Change N to or, what happens?
If you change the and to an or, then it won't work anymore. Because if you change the and to an or, first of all, it won't get out of the loop. You know, it will only get out of, okay, so if you think about it, the reason to stay in the loop is I haven't seen everything yet in the array, which is what the left-hand side is saying, and or what I'm looking at is not what I want to find. So you won't be getting out of the loop. In fact, if you turn this into an or, this program will try to access, an element that does not exist, which is not a good condition to have. Is that okay? Are we good with this construct? Okay. But we still have a big question to ask, which is, I know the algorithm is exiting just fine in this case, and if we do find something, it will still exit correctly. But the question is, how can I tell whether I found what I was looking for or not? So what do you look at after the end while? If I want to add some code here, okay, so I'm gonna add some code here, and I will let you guys tell me what this particular C condition is, so that on line 6 I can say print confirmed, okay, found, okay, and then on line 7 is else. On line 8 we print not found, and line 9 is and if. In other words, from line 5 to line 9, all I want to do is to give the end user a feedback of whether K is found in array A or not. Okay? So the question is, what do you use in C to make that determination?
Like K equal to AI,
Say that one more time.
K is equal to
Okay. So let's think about that. Okay? So one proposal is, what if we use this, right? Do you think there might be a problem with this? What if K is not in array A?
it just exit.
No, I wanted to print not found. Okay, so if we use this as a solution and we have a test case like the one that we just did, okay, and we have a test case like this, just kind of imagine by the time we get to line 5, what is going to be the value of I? So we are not doing post yet, because we are not done. So after line 2, we get to line 5. On line 5, what is the value of I?
3.
No.
Doesn't exist.
No, okay, fine. Let me just do this, okay? Because we are just extending the length of the program, so we are just removing the post and turn this into 5, right? So after the loop, we continue execution on line 5, and line 5 wants to evaluate the condition. That condition is k equals to a bracket I. Do we have a problem here?
Yes.
And the problem is
A bracket I is index 2, which is out of bounds.
exactly, because I is 2, so a bracket 2 does not exist. We are trying to index the array out of bound again. Okay, so k equals to a bracket I is not going to solve the problem. Okay, but good try. Okay, very good try. Except it doesn't work because I can be out of bound already at this point. So that particular clue is telling us that maybe we should not be indexing using I. Okay, but we still need to use I because that's one clue we can use. K is not going to be very useful because the only way to use K is to compare it against an element of the array, and we already know that we should not be indexing into the array because I can be out of bound at this point. So K is out of the question. Putting I in square bracket is out of the question, but I itself is going to be a key in this particular comparison. Okay? So what else can we do with I?
Oh, if I is greater than,
I think you meant less than
yes.
bar a bar.
Bar A bar, yeah.
That's it.
That's what I
Okay.
was trying to say.
Yep. So that's right. Okay, so this is the right way to do it. Because on line 5, if I is still less than bar a bar, what did it tell you about the reason why I got out of the loop? K equals a bracket I, which means I found it. Yes? Let me say that one more time, okay? So I'm trying to reverse the execution of the program. On line 5, the condition is I is less than bar a bar. Do we all agree that this can be evaluated without a problem after the loop? Yes, because I is just a normal variable. I'm not using it inside a square bracket, which means I'm not using it as an index into the array, which means I cannot be addressing I cannot be specifying an element out of bound. Bar a bar is really just the size of the array. So we have an integer on one side, another integer on the other side. It's always okay to compare those two integers. So this is not going to give us any problem as far as the evaluation is concerned. But what does it mean when I is less than bar a bar is still true at this point? Okay, well, the consequence is we're going to go to line 6 and print found. But how did we get out of the loop if I is still less than bar a bar? That was the question. Because the reason to stay in the loop is I is less than bar a bar and K is different from a bracket I. So after the loop, if I can still confirm that A is less than bar a bar, what would be the reason that I got out of the loop? The second condition of the conjunction is false. Does that make sense? Yes? Okay. But what does it mean when K is different from a bracket I is false? That's just a really long and clumsy way to say that K equals a bracket I, right? So if K equals bracket I, didn't that just confirm that I just found an element with the same value as K? That is how it works, okay? But we also have to kind of double check and make sure that if I is not less than bar a bar, it means that we did not find the element, okay? Does that make sense? The question is, does that make sense? Well, what does it mean when I is greater than or equal to bar a bar? Knowing that I started off with 0. It's index out of bound, but in the process of getting the index out of bound, I have examined every single element already in the array. And none of those matched K, because if anyone had matched K, I would have exited when I was still less than bar A bar. Is that okay? So that means if I is less than bar A bar is false on line 5, I have confirmed that I did not find K in the array. Is that okay? Okay, some of you are nodding and some of you are going like, I need more time to process, which is okay. And that's partially why the lecture is recorded. Okay, so you might want to just kind of write down the timestamp and say, okay, I kind of need to chew on that part a little bit more, a little bit later in the day or before next Tuesday. But this does work. Okay. Are we okay with this algorithm? Are there any questions about this algorithm as it is right now? And I mean, as it is this particular version. We're good? Okay, all right. So this algorithm is known as linear search. Linear search is kind of like we start from page 1, and then we look through page 1 sequentially, then we look at page 2, through page 2 sequentially, then we look at page 3 sequentially, and so on. Okay? If I give you a okay, this may not be a very good example because who used a phone book in last 2 years? Nobody. Okay, see. How about a paper-based dictionary? Okay, someone had used a dictionary recently. Okay, very good. But does everybody understand what a dictionary is? I mean the paper organic version. Yes, we know what it looks like? Okay, good. So I want you to look up, okay, just pretend, okay? I want you to pretend to look up the word orange, okay? O-R-A-N-G-E, okay? How are you going to search for that word in a dictionary? Are you going to start on page 1? So you start with A, go through the whole page, go to the next page of A, go through the whole page, and in about 3 hours or so, you'll get to O. Exactly. So we don't start from the beginning, okay? So this particular search method, which is basically saying, okay, you want me to look for zebra? Sure, I'll start on page 1 of the dictionary. Start with all the A's, and then move on to all the B's, and move on to all the C's, and then at the end of the week, I might find zebra. Okay? It's not very efficient, is it? And this is definitely not how we do things. So the next method of searching for something relies on the array itself being sorted. Do we all understand what is sorted versus not sorted? Okay? Not sorted means things can be out of order. Okay? At least one part of the whole thing is out of order. That makes the entire thing out of order. Sorted means everything is in order. Now, what order are we talking about? Are we talking about in increasing order, decreasing order? It doesn't really matter, okay? When we say it's sorted, we just means that pick one ordering method, but the entire thing, the entire array is ordered using that particular criterion. So are we good so far in terms of defining what I mean by sorted? Yes? Okay. So let's say so I can illustrate an example using a spreadsheet. So let's go to a spreadsheet and I will give you an example. Okay, so let's say we have 1, 6, 7, 10, 11, 14, 14 again. And let's make a whole bunch of 14s, because it doesn't really matter when we have repetitions. But we want to get it up to 15 items. 45, 50, and we can skip by large amounts, not a problem. Okay, and we get to 20,000. Okay, there we go. So I would just pretend that this is an array, okay, and I want to do a search, and I want to look for a particular item here. If I want to use a particular algorithm to search for a particular value, okay, what do you think is the minimum number of comparisons to confirm that something is not in the array? Using linear search, it would be 15 because you really have to compare every single one before you can confirm that it is not in the array. Okay, but that's only linear search. But if I let you use any structured search mechanism, what would be the number of comparisons that you need to confirm that something is not in the array? Yes?
One,
Why would it be 1?
because you can just say choose a random number and it could just happen to get the right one.
Okay, but I want to confirm something is not in the array. So with one comparison, yes, you can confirm a particular element is not what we want. But what about the other 14 elements? You have no idea of whether those other 14 elements has the value that we are looking for. So we cannot do it with 1. I'll give you the answer. 4. Okay? That's a very good question. I like that. I like people asking, why? Well, I'll show you, okay? All right, so I can show you different examples. So you might want to mark the time, which is, okay, that clock is not always reliable. It's 2:25 right now, so you might want to write down because this is the beginning of a demonstration that you might want to refer to kind of from time to time. So give me a value that is not in the array so I can show you why I can make that conclusion in only 4 comparisons. Okay, hands up, hands up. Okay, you're fast. 90, okay. So we are looking for 90 in this case. So k equals 90. So what I do is I start from the beginning of the entire thing. Now, with 15 items in the array, which one is the center? Which one is right in the middle of the entire array? The one that is, okay, which row, okay, is going to be at the right in the middle? No. This one. This one is dead in the center because it has 7 elements before and 7 elements after. Does it make sense? Because 1 plus 7 times 2 is 15. Yes? Okay. So we look at this one and we ask, does 14 equal to 90? Am I lucky that I just stepped on the value that I want to look for? No, because we picked something that was not in the array, right? So instead of just saying that 90 does not equal to 14, I can get more information. Is 14 less than or greater than 90? It's less than, right? Okay, cool. So we make a conclusion that 14 is less than 90. Does it make sense? Okay. Doesn't seem like it's going to help us. Oh, it helps tremendously. Because knowing that 14 is less than 90, and also knowing the array is sorted in a non-decreasing order, what do I know about all the elements before this particular 14? They're all less than 90. Without any additional comparison, I have just eliminated all of these guys. None of them can be 90. Does that make sense to you? Yes?
But in say when you're tracing, would they all be like in order like that? Like numerically?
So you do need the array to be sorted before your algorithm starts. That's an assumption you need in order for this method to work. Okay? So now I can eliminate this portion. So to mark that I have eliminated this portion, I am just going to highlight all of these with a particular color. Let's say gray. Okay, I'm graying out all of these. Okay? So knowing that from here to here cannot be the value I'm looking for, what would be the next element that I should compare to? In other words, I only got 7 elements left that can potentially have the value that I'm looking for. Which one of the 7 should I compare to? The middle one. Okay, very good. Of the 7, which one is the middle? This one, right? Because this is the middle one. It has 3 before and 3 after. That makes it the middle one. How does 50 and 90 compare? 50 is less than 90, right? Okay. But because the array is sorted, what do I know about all the elements before this one? They're all less than 90 too, right? Okay, so what can I eliminate at this point? All of these guys. Okay, so once again, mark them gray. Now I got 3 elements left. Which one should I choose to compare? The one in the middle, which is the one 10,001, right? So I look at this and go like, oh, wait, hold on a second here. This one is actually greater than 90. That's good, because now I know not only this element does not equal to 90, but everything after that cannot be 90 either. Does that make any sense? So I can now mark these two and eliminate those. I have only one element left, which is this one here, and 1000 is also greater than 90. So now at this point, I mark this and everything after that to be eliminated. I think I have just eliminated every single element at this point. So I can make the conclusion and go like, none of these elements has a value of 90. How many comparisons have I done? Exactly 4. This is called the binary search. Do we want to run this through with another number? You guys can pick something a little bit trickier, like 13. Do we want to go for another run? Yes? Yes? No? Yes? Okay, let's go for another one. Okay. So let's go for another one. I'll keep this one around, okay, so we can refer back to it if somebody has any question. So we'll keep the array, but this time we're looking for 13. Does anyone have a problem with the unlucky number 13? I'm sure every number is unlucky in some culture and some religion and some family. So let's not think in that from that perspective. Okay, so we're looking for the number 13. Once again, where do we start? In the middle. Very good. Okay, so the middle one is this guy, and we say darn close but not quite. Okay, 13 is less than 14. But the useful part is we also know this entire portion. Okay, this entire portion is also greater than what we are looking for. Does that make sense? Because we are given that the array is sorted in a non-decreasing way. So if this cell, if this particular element is greater than 13, which is what we are looking for, everything after that is already ruled out. Okay? Okay. All right, so we just mark those as ruled out. What do we compare to next? The element on which row? 4. Row 4. Very good. Okay, so we look at this one and say, you're next. 10 is less than 13, which is what we are looking for. So which part can we eliminate because of this? Everything before, okay? So this guy and everything before can now be eliminated. We got 3 elements left. These are the only 3 left. Which one should I compare to next? The middle one, which is the one on row 6. Very good. And we say, not quite. So that means this element, along with everything after that, can now be eliminated. Right? In the 4th and last comparison, we only have 1 left. Okay? And we say, that's 11, and 11 is less than 13. Also not what we want. So now what we can rule out would be this and everything before that. But we have just eliminated everything at this point. So the conclusion is, sorry, 13 is not a part of the array. Yes?
So is the number of comparisons you need, no matter how many elements are in the array, always 4?
That would not be correct, because if I double the number of elements in the array, I would have to add 1 comparison. So let's think about it, okay? What if I give you 31 elements in the array? Okay, think about it. So if I give you 31 elements in the array, I use the same approach. I choose the one right in the middle to compare, right? Now, let's just say that, I'm looking for something that is not in the array. So the element in the middle of the 31, is not what I want, okay? What can you conclude from that inequality, which is either less than or greater than? You can either get rid of that one in the middle and everything before with 15 remaining, or you can get rid of the one in the middle and everything after that, but also with 15 remaining. then it boils down to the same question as what we are solving now, because we have 15 possible elements that can have the value. This one takes 4 comparisons. But to get to this point from 31 elements, we need 1 comparison. So if I have 31 elements to begin with, I will need 5 comparisons to conclude that an element is not in the array. Is that okay? What about 63? If I have 63 elements, how many comparisons do I need? 6 comparisons. Because it will take 1 comparison to cut it down to 31, and then it will take another comparison to cut it down to 15, and we already know that by the time we get to 15, we only need 4 comparisons. Is that okay? What do you think is the next step up from 63? I think some people are starting to notice the pattern.
120, whatever.
Not 120 something is right, but not 128.
24.
No. Okay, let's look at this sequence here. This is not an IQ test, but it does kind of test whether you can detect like a pattern. So we start with 1, which is kind of obvious, right? With 1 element, I need exactly 1 comparison to confirm that the only element in the array is not what I want, right? With 3 elements, I would do 2 comparisons. With 1 comparison, I will eliminate 2 of the 3, and then I need 1 more comparison for the leftover, right? So this is the sequence: 1, 3, 7, 15, 31, 63. What is the next one?
127.
127, very good. And how did you get to 127?
You added times 2 plus 1.
Times 2 plus 1, very good. Okay, that is exactly what we do. Well, okay, so technically speaking, there's a 0 too. But it's not a very useful one, that's why I did not list it. But yes, so technically speaking, we start with a 0. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 3 times 2 plus 1 is 7 times 2 plus 1. 15 times 2 plus 1. 32 times 2 plus 1. 63 times 2 plus 1 is 127. So the next one up is in fact 127. And let's see, we'll just work it up a little bit here. Next one is 255, 511, 1023, 2047, 4095, and so on. Okay. If you just look at the kind of the overall picture of the thing, what is the rate of increase if I were to plot this out on a graph paper? Exponential, very good. Okay, it's almost like doubling, except it's almost doubling, but not quite, right?
It's like 2 to the power of n minus 1.
You are so wrong. It is exactly like that. I'm just toying with you. No, you were absolutely right, okay? It is exactly 2 to the power of something minus 1. 2 to the power of 0 minus 1. 2 to the power of 1 minus 1. 2 to the power of 2 minus 1. 2 to the power of 3 minus 1, and so on. That indeed is the right pattern. Very good. I like that. So what is the big deal about this search algorithm? What is the Earth's population right now, people-wise? Let's call it 8 billion, okay? So let's just say that I have a super huge, gigantic directory of every single person on Earth right now, okay? So it has 8 billion entries, right? How do I confirm that someone is not on that book? Like Mr. Spock would not be in that directory because he's Vulcan, he's not Earth from Earth. So how many comparisons do I need to confirm something is not in an array that has 8 billion entries? Now you guys would probably think, oh, Tag, you must have memorized this answer. No, I do not have the answer memorized, but I can derive it step by step. Okay, so let's think about this a little bit, okay? So we are talking about 8 billion or thereabout. Okay, is that 8 million, that's 8 billion. Okay. So the question is, how many times can I divide this by 2 until I get to a fraction that is less than 1? That's basically is what we're asking, okay? So you can solve this question, you can solve this problem by a few ways. You can use a calculator, okay? And enter 8 billion, okay? Divided by 2, look at it, oh, not the answer. Divided by 2 again, nope. Divided by 2 again, and keep dividing until you get to a number that is less than 1. That's one way to do it. But remember, you have to keep track of how many times you have divided by 2. Okay, so that's repetitive, but it's doable. Okay, sorry? 33. Okay, 33 is what you want. Okay, so but I'm looking into the way to do it. So what you did probably is using log, right? You take the log, you take the natural log of this, and you divide that by the 2's natural log, and that will give you an integer. And that, if you round that integer up to the next available integer, that will tell you how many times you have to compare. Because the log divided by the other log is what, 32 something, right? Yeah, so you have to take the ceiling of that, which means you step up to the next available integer, which is 33. So those are all kind of math heavy, intensive kind of thing. I'll give you a quick trick to do this, okay? Because what we are looking for is some power of 2 that is greater than or equal to 8 billion, okay? In other words, if I raise 2 to some power p, I want this to be just barely greater than or equal to 8 billion. I want to find what that p is. Is that okay? Does everybody feel comfortable with exponents? Yeah. Okay, very good. So I'm just borrowing the caret symbol here to mean superscript, which is exponent, okay? So the way I can do this really quickly is to use a few tricks, okay? One trick that I use is 2 to the power of 10 is exactly 1024, which is approximately 1000, which is exactly 10 to the power of 3. Now this is a very useful rule of thumb to use when you just need to estimate something, okay? So knowing this, I need to rewrite 8 billion, right? So 8 billion is exactly 8 times 10 to the power of to the third, and that to the power of 3 again. Is that okay? Yeah. Yep. Okay. So I'm hoping you guys are still comfortable with your exponent math, because raising 10 to the power to the third is basically multiplying the 2 3 that would end up with the 9 zeros that we have here. Is that okay? So using the approximation, I can now say that this is approximately 8 times, and this is where I substitute 2 to the power of 10 in place of 10 to the power of 3. Is that okay? That's just approximation. So given this approximation, the next line is exactly the same as the previous line, so I'm not using approximation anymore. I should actually do it like this, okay? Okay, this is exactly 8 times 2 to the power of what again? How do we combine the 10 and the 3? 30. We multiply those two because it is 10, it's 2 to the power of 10, the whole thing to the power of 3. So we multiply those two powers. So we have 2 to the power of 30. But hold on a second here. Isn't 8 also a power of 3? Yep. Okay. So 2 to the power of 3 times 2 to the power of 30. This time we add the exponents because we have a multiplication. So we have 2 to the power of 33. That's why it only takes 33 comparisons to confirm a particular item is not in an array of 8 billion items. That is pretty cool. Nobody seems to be convinced to be impressed at all by this math here. I am totally impressed. This is like the nth time I've taught this class, and I'm still impressed. Okay? You have, what about 16 billion? What if the world population is to double again? Because we start to colonize Mars and Venus at the same time. Huh? 34. Then it would take 34 comparisons. Every time we double the size of the array, we add 1. to the number of comparisons. That is super cool. Okay, no one seems to be convinced at all. It's like, I have no idea what you're talking about. Why is this impressive? Isn't this impressive? You have this huge, gigantic array of 8 billion entries. I give you something to search and say, is this thing in the array? You only need to have 33 comparisons, as in 1, 2, 3, 4, 5, 6, all the way count to 33, and you can confirm it is not in the array. If it is in the array in 33 comparisons, you would have found it. That is really cool. Okay, some people seem to be convinced because I think some of you are thinking, if we don't convince Tech that we are actually convinced this is cool, he will never let us go. Yes.
You are talking about that 64-bit computer, right?
Yeah.
Is the 64 is like 2 to the power of 64?
So with 64-bit, we can represent values up to 2 to the power of 64 minus 1, which is a huge number. If you convert that number into base 10, it would be 13 with 18 zeros after that.
Is that like you can do that 2 to the power of 64 minus 1 computation in 1 second?
No, not quite. 64-bit means we can do math calculations with 64-bit integers, at a very high speed.
Okay,
Yep.
so can we do this 8 billion bit calculation really high in our regular computer?
Okay, so if you are looking into the performance of modern day computers, with a multi-core processor like an i5 or i7, and each core actually has multiple ALUs, so they can actually carry on multiple integer computations at the same time. So if your question is asking, can we perform 8 billion comparisons in a second? The answer is yes. But 33 comparisons still beats 8 billion comparisons. Yeah. Yeah, so let's see, how much time do we have left? I think we still got a few minutes. Yeah, we got 3 minutes left. So the question now is, well, if this search method, okay, we haven't really talked about the algorithm yet. So if this search method is so much faster than linear search, okay, do you think it is important to know which algorithm to use? Okay, so I got a yes. Is that true even when computers are getting faster and faster and faster anyway? The answer is also yes. Very good. So next class, I will use this, I will compare binary search, which is what we just did, okay? And we'll compare that to linear search. And we'll have a very interesting race, okay? We'll have this kind of fictional scenario where Tech and Pat, okay, are the only 2 software engineers left because a company is downsizing, okay? And there's a programming contest to decide who is going to be let go because their program is running slower. Tech is still using an old computer from the early 90s, whereas Pat has a top of the line current computer with a bazillion gigahertz processor, okay? So the question is, if Tech is using binary search and Pat is using linear search, first of all, can Tech actually beat Pat? Okay. The second question is, if that is possible, what it would be the size of the array that we have to tackle in order for Tech's computer, really, really slow computer from the early 90s, to beat Pat's computer, which is a super fast modern day computer. Okay. So we'll go over that on next Tuesday, because that discussion will help convince you, why understanding algorithms is very important if you want to keep your job. Okay? So we have homework over the weekend, and then we'll continue this topic after the weekend.
Zach, is the homework
Yep.
due Tuesday or Thursday?
It's due in a week.